Have you ever thought about what a modern chemical plant really is? It's not just a jungle of pipes and tanks. It's more like a vast, complex orchestra. You've got thousands of instruments, all those pumps and heaters and valves, and they all have to play in perfect harmony 24/7 to create the products we use every single day. So, who's the conductor?
And that's really the core problem for a process control engineer, isn't it? How do you manage a system where every single tiny adjustment can send ripples through the whole thing and maybe even throw the entire performance into chaos? All right, let's get into it.
So here's our game plan. First, we're going to unpack this whole industrial control puzzle. Then, we'll figure out what our goals are and what tools we have, our knobs and gauges. After that, we'll tackle what's called the perfect pairing problem, discover a really cool way to score the best connections, and finally, we'll zoom out and look beyond simple control to the big world of optimization.
Okay, let's kick things off with a fundamental challenge here. In any complex process, things are, they're rarely simple. Turning one knob almost always affects something else, and really wrapping your head around that is the key to everything.
This slide really gets to the heart of it. On the one hand, you have a simple, what we call a CISO system. Single input, single output. That's easy. One knob controls one gauge. But most big industrial processes, they're MOMO systems, multiple input, multiple output. And you've probably experienced this. Think of a cranky old shower. You turn up the hot water knob, and sure, the temperature changes, but the water pressure drops too. Every knob seems to affect every gauge.
And this whole tangled mess actually has a name. It's called process interaction. It is the defining challenge of controlling these big, multivariable systems. It's that ripple effect we talked about, where one single action has multiple and sometimes totally unintended consequences. This is what engineers are paid to master. So if you're an engineer staring at this beast of a system, where do you even begin? Well, the very first step is to break the problem down into its most basic parts. What are we trying to accomplish? What can we measure? And what levers can we actually pull?
Before you even think about touching a dial, you have to know what you're trying to do. And it's always a balancing act. Safety is the absolute #1 priority. That is non-negotiable. After that, you're juggling environmental rules, making sure the product quality is right, and of course, running the plant profitably. The goal is to keep the entire operation running smoothly and stably inside all of those constraints.
To make this all feel a bit more real, let's use a classic example that pretty much every chemical engineer both knows and, let's be honest, kind of fears: the distillation column. It's the perfect case study because it's absolutely essential for separating chemicals, but it is notoriously difficult to control.
And here is that MIMO problem in a nutshell. For a typical column, we have at least 5 gauges, or controlled variables, that we need to keep right on target. And to do that, we have 5 knobs, or manipulated variables, that we can turn. But here's the catch. Pretty much every single one of these knobs affects most, if not all, of the gauges.
So we've got our 5 knobs and our 5 gauges. The next question seems simple, but it is deceptively complex. How do you pair them up? Which knob should be responsible for which gauge?
I mean, for a system with just 5 inputs and 5 outputs, you might think, how many ways can there really be? Well, the math works out to 5 factorial. That is 120 different possible control configurations. Choosing the right one is absolutely critical.
And the stakes here could not be higher. I mean, picking a bad pairing doesn't just mean you're being a little inefficient. A really bad pairing can create control loops that are literally fighting each other, leading to wild swings, and in the worst-case scenario, a completely unstable and unsafe plant.
So, how on earth do you sort through 120 different possibilities to find the one that's going to be stable and work the best? Well, you don't guess. You use a brilliant engineering tool that was designed for exactly this problem.
It's called the relative gain array, or RGA for short. It was invented way back in the 1960s, and it's basically a mathematical way to measure that process interaction we talked about. You can almost think of it like a compatibility score from a dating app, but for industrial controls. It tells you which knob and gauge are the most natural fit for each other.
And what the RGA does is it spits out all these scores and organizes them into a nice, simple grid. Each number in this grid, represented here by the Greek letter lambda, tells you the compatibility score between one specific gauge, like Y1, and one specific knob, like U1.
And the best part is, rating the score is surprisingly intuitive. If the score is close to 1, boom, you've got a perfect match with very little interaction. If it's between 0 and 1, the loops actually help each other out, which is pretty good. But if the score is greater than 1, they start working against each other. And a negative score? Oh, that's a huge red flag. That means the loops will actively fight, which leads to instability. You avoid those pairings no matter what.
So this all leads to a simple but really powerful rule from the inventor himself. You want to pair up your variables so that their relative gains are positive and as close to 1 as you can possibly get. It's just such an elegant solution to an incredibly messy problem.
Now, this pairing strategy is fantastic for a single piece of equipment. But what happens when you zoom out? What about the entire plant, where everything is connected to everything else?
Well, sometimes, even with the best pairing you can find, significant interaction is just unavoidable. It's just the nature of the process. In those cases, engineers have another trick up their sleeve, a special kind of controller called a decoupler. Its entire job is to predict the interference coming from one control loop and then proactively cancel it out before it has a chance to mess up another loop. It's pretty clever.
You know, it's cool to see how this all fits into the bigger picture, because everything we've been talking about, the MIMO control, the pairing, the RGA, that all fits into level 3 of a much larger control hierarchy. Below that, you've got your basic single loops and safety systems, but above it, you've got layers that coordinate whole sections of the plant. And at the very top, you have real-time optimization that's constantly tweaking targets to maximize profit and efficiency for the entire company.
So the next time you use fuel in your car, or take medication, or even just open a package of food, maybe take a second to remember this invisible orchestra. It's this incredible symphony of math and engineering, all working silently in the background to conduct these massive industrial processes safely and efficiently.
It's a system that's been built on decades of human ingenuity. But, you know, it leaves us with a fascinating, kind of wild question for the future. What happens when we hand the conductor's baton over to an AI? One that's capable of calculating every single interaction and optimizing the entire orchestra in real time. What new kinds of symphonies will it compose?